Thanks for coming to this talk about my favorite topic at the moment, graph machine learning. And especially I want to talk about it when to use it, but also probably even more important when not to use it. So what is GraphML all about? I would kind of say it's the future of AI, kind of from a marketing perspective, but really looking at what's happening. For example, let's take Uber, doing predictions with that. Let's taking the latest machine learning conferences, NeurIPS, about like 30% of the papers mention graph in one way or the other. Let's take a look at what Google is doing. It's actually happening a lot about graph, and we'll learn about why it actually makes sense. But I think the statement here is really bringing it down to like relationships. Let's take relationships as first-class citizens, and then actually we can make much more sense out of our data. So that was kind of the marketing for GraphML, but on the other hand, I also want to caution you when not to use it. So for example, looking at this conference, we have a bunch of talks about graph data science, about graph machine learning. If we look at, as said, like Uber is publishing a lot there, DeepMind on the Google side is publishing a lot about that, but is it really something like the all-solving tool we should apply everywhere? So I think that is kind of the second part of this talk. Me, that's Jorg. I'm currently CTO at ArangoDB, so scalable graph database company. In my past, I pretty much built like a lot of data infrastructure for machine learning, for data science. So this is why I'm particularly happy that right now I can combine all those passions from databases, large-scale distributed systems, and machine learning within one role. Why do we care at ArangoDB? So ArangoDB is a scalable graph database which also supports other data models. So a lot of the use cases we're seeing both from our customers but also community, of course, being open source, are around graph analytics, are around graph machine learning, and I think this is why I'm particularly happy and so excited about this topic. If you haven't encountered graph before, let's briefly talk about why graph makes sense, maybe from a database point of view first. So I often get this question like, when should I use a relational database? When should I use a graph database? When basically the market is kind of in this NoSQL space also growing quite a bit. And my answer is usually try to look at your data access pattern. If I'm accessing it either like row levels, so for example here products, if I'm just inserting individual products and all I'm interested in is looking up individual products, great. Relational database, SQL, perfect. If I'm on the other hand, if I'm interested in aggregating, for example, over the price column, again, I'm just looking at like one part of the data, kind of not in a row format, but in a column format. Again, column stores are pretty good at that. But what I'm usually, or very often interested in is actually like more complex relationships between the data sets. So for example here, talking about co-purchasing pattern in between different products. So as soon as I'm not interested in individual products or individual columns, relationships are becoming very important to analyze, and they're just, SQL databases have like a certain limit because joins don't really scale up very well, and this is where then graph databases are coming into the play. And this is also what we at ArangoDB really see as relationships being the first-class citizens out there, and this is also what we see as kind of this foundation to this new data analytics, to this new data machine learning on connected data. All right. Where do we now go from graph databases, as said, ArangoDB, towards graph machine learning? I think it's actually like a kind of chain of different use cases. So on the simple end, we're starting with like a graph query. Any graph database can handle that. Who can introduce me to a certain person? And you might have seen that on LinkedIn. You might have seen that on Facebook or wherever. You get like a prediction like, hey, you should talk to this person, and this is the one who can connect you to them. So this is usually constrained on like a small part of the overall graph, and we are looking, for example, for a path. Easy graph query. Next step, next level is graph analytics. In graph analytics, I typically want to answer questions about the entirety of the graph. So for example, who is the most connected person? We can then get into details what means most connected, because there are many different distinctions, but I think we want to get like a property, an insight of the overall graph here. Then the next level is actually about graph machine learning. Here we are switching from analytical models to statistical models, and we're actually training a machine learning model there. So with that, we can answer questions like predicting new potential connections, or also, as it's called, edge predictions. We are trying to predict like a missing edge in the overall graph. We can do node classification, so for example, trying to predict churn in this overall graph. And I think this is actually also where I see the value of graph machine learning and even graph analytics, because we are going beyond an individual record. If you're familiar with more, let's call it traditional machine learning, we often have this assumption of independent data. What does it mean? If we take here, for example, your favorite social network and you're trying to predict churn, who's next going to leave the network, so you can send more marketing outreach, you can connect to them and trying to keep them in the network. If we use traditional machine learning, we actually would have a feature vector for each individual user, and then from that feature vector, we would try to predict the churn risk out there. In real world, just imagine like all your friends have left Facebook, all your direct connections have left your favorite social network. What does it do with your own risk of leaving that network as well? Obviously it goes up for two reasons. First being, all your friends have just left. The value of the network just decreased for you massively. On the other hand, probably you have similar reasons to leave that network as well. And that's actually an assumption which we see in a lot of connected real-world data sets, which is called homophilia, that neighboring nodes often share similar attributes. And this is something we often miss in traditional machine learning, kind of that value of the data we have in the relations or in our direct neighborhood. Obviously, I can go in and build that, and we'll see that on one of the next slides, but this is something we often miss in traditional machine learning. Those assumptions, this value, these properties we have in real-world connected data sets. What are kind of the innovators doing there, or to which areas can I apply graph machine learning? I can apply it to a bunch of different areas. We see a lot happening in supply chain, we see a lot happening in recommendation and search. For example, Uber has a really great blog post about that. Computational chemistry, drug discovery. Again, if you think about a molecule, it's a graph in the end as well, and we're trying to predict certain properties of it. And then also in financial services, risk prediction and fraud detection are use cases where we have connected data sets and we can apply machine learning to them to have benefits from that. So, as mentioned, we can also do that with more traditional machine learning if we build explicit features. So, going back to the example of trying to predict churn, I might take my graph, I might build an extra feature saying like, hey, how many of my direct connections have left that network within the last month, and then use that feature to enrich that, to enrich my input to whatever machine learning task I have. This is called explicit feature engineering, and I need someone doing that, and then I also need to maintain that feature. So it's actually quite costly. But can be done. And the beauty now of graph machine learning is that we actually get that value of the neighborhood implicitly in our machine learning. So we don't have to do that explicit step of scoping out those features. I get it implicitly from the neighborhood. So in short, GraphML is applying statistical methods, training a model to graph-based data. And I can use that in both in supervised and unsupervised setting out there. So, foundations of a lot of that are graph neural networks. I don't want to go like into too much detail, but in the end you can imagine you're building like a latent, like a new representation of your graph, and that can be optimized for tasks like node classification, entire graph classification, where I'm not only considering a single node, but for example a molecule, and I want to say like those two molecules are most likely the same or share certain properties. And then I can also use it for link prediction. That is, for example, the task of recommending like, hey, you should connect these two nodes in your network. Nowadays, there are a bunch of different architectures, and also looking at machine learning conferences, there are new things coming out every day, so it's a really fascinating field to follow. But I think what I just want to kind of like give you is, if you compare different architectures, there are certain properties you should look at. So for example, here's those two columns, like homogeneous versus heterogeneous networks. Sounds complex, but in the end it comes down to, do I just have a graph where all the nodes are the same, so for example users being connected to users, or do I have a more complex knowledge graph out there where I have like different node types like users, rating movies, movies being in there, etc., etc. So where actually not all the node types are being the same, and that has an implication on what kind of machine learning models you can use. On the other hand, for practical purposes, a pretty important property is transductive versus inductive machine learning. Transductive is basically means we have to, as soon as we get like new data, as soon as we want to apply it to previously unseen data, we have to retrain our model. So it doesn't apply to new data out of the box. And this is really a nice property of inductive architectures, where I can go in and apply it to previously unseen data. So you can already see this is quite important for scaling that out. Okay, this is kind of the new shiny world. But there also has been graph analytics, which has been around for quite a long time. So that is analytics applied to graph-based data, and it can often apply to pretty similar areas. So again, from like marketing, fraud detection, supply chain, etc. Often I have a choice whether I want to use something on the graph machine learning and or on the graph analytics front. So we'll learn about where the difference is, but maybe just to like show some examples about different graph algorithms which can be applied there. For example, from like search, finding a particular node or edge, to path finding, which would be our example earlier, who can introduce me to which person. That comes down to finding a path in the overall graph. Then we have the notion of centrality, fancy term for saying like, what are important nodes in my graph? And there we can already see we have, on the right, we have a lot of different definitions of what it means to be a central node in that graph, what it means to be like an important node in that overall graph. Then we have cycle detection. We try to find like cycles within our graph, or we also have that task of community detection, just to show like some of the fields where graph algorithms exist and have existed for quite a long time. And yeah, as already mentioned, like in the different use cases, we have quite some overlap. We have certain use cases where we can just apply graph analytics or just apply graph machine learning, but that vast majority actually allows us a choice in between. And so we as data analysts, we as data scientists, we actually have to make a choice in between. And to have like one concrete example, at ArangoDB, we have this demo or internal service called ArangoFlix, which is a movie recommendation service. Especially in pandemic times, we needed to figure out which movie to watch next, so we built ArangoFlix to actually give us movie predictions. And so there we have a number of different options, and I don't even want to go like into too much detail. I just want to tell you for this recommendation task, we can already apply things like document, term frequency, inverse document frequency. We can use analytic methods called collaborative filtering. We can use graph embeddings, which then we're already in the machine learning world, or at least at the kind of frontier about that. Or we can also use the graph neural network directly for doing link prediction, because in the end, if you think about it, recommendation, it's about predicting a link between a user and a movie there, which you might want to watch. So that, of course, then comes down to how should we actually choose in between those two. And there I try to kind of like list the main criteria out there. So I think the first big one, and we'll dive into more detail there, is about performance. And interestingly, about performance at different stages in the cycle. Next one is about accuracy, reproducibility, and approximation. So can I live with actually like incorrect results? As statistical machine learning, it's statistical in the end. So I always live with a kind of approximation, which might also be good for us because it actually generalizes beyond the data set we're just seeing. Next kind of point we should ask ourselves when choosing in between is about explainability. How well do I need to be able to rationalize about the outcomes I'm seeing, about the inference, the recommendation I might get out of that system? Next question is then about scalability. To which kind of data set size does it need to scale? To which kind of like dynamic progress, so how often do I update my data set? Does my solution need to scale? And then of course also like which data do I have available? If I'm training a machine learning model, I obviously need some kind of like annotated data available. So that's also on that front a criteria. But let's go into more details here. So I think first and probably biggest one is about performance. Graph analytics, and that's probably like one of the big kind of like hindrances to larger adoptions. It depends on the algorithm, but in general it really grows with graph size. So those large graph analytics, I really have to see how can I scale it out. So we in ArangoDB, we use like a framework originally proposed by Google called Pregel for that, where we can scale it out across multiple nodes, but of course it still needs to scale with like the graph size out there. Typically, graph analytics is transductive by nature. So again, to recap, that means I need to recompute that, I need to rerun the analytics. As soon as I have like a new query, as soon as I'm updating my graph, or I'm seeing like previously an unseen graph, so new data basically means recompute. Graph machine learning, on the other hand, allows me to split the performance into two different points. I have the training part, which often can be done offline, and then the inference part when I actually need an answer. So this is a really nice property for a lot of machine learning, or for a lot of tasks where I want to apply that when I ask the question, I don't have to do all the work, but I can basically do that training up front and then just leverage the model for inference. On the other side then is also the inductive nature of modern graph machine learning. The first models, they weren't inductive by nature, but like most of the modern graph machine learning is actually inductive by nature. So it also means it's like constant kind of in graph size, because I only look like at a certain neighborhood. I don't have to feed the entire graph in there, which then also we'll see when we talk about scaling. The kind of performance, obviously it depends on model complexity. I can build very complex models, which even for inference take a lot of time, but I can do that trade-off kind of like very consciously, like how complex should my model be, how much data do I have available to train it, how much time do I have available, or how much resources do I have available when doing the inference. So bottom line is actually inference, so our actual query to the model is much faster compared to graph analytics. Next point is about accuracy and approximation, and that comes down to, do I need like exact results out there? So, or is an approximation sufficient? I worked in like graph or ML space connected to healthcare, AI and healthcare before, and there it often was like really important that we could also go in and justify where something was coming from. Of course, a doctor is not going to like if you tell them, hey, this outcome is only probable with like a certain margin of error, or at least that should be like very small. So it comes down to like how accurate something is. Analytical models are very accurate and can reason about it, but they, as we learned before, might just be too expensive to actually run at scale. Graph machine learning, on the other hand, by nature is statistical model, so it's an approximation, and there I have to do, again, I kind of have like those knobs to take care of the complexity between like size of the model and the quality of the outcome I get. So I kind of can control for the accuracy of the model, but it still remains an approximation. Keep in mind, typically, this is fine for most use cases. Explainability. Again, also connected to this, how reproducible can I get results, and how much can I reason about how did I get to results. Again, in like healthcare space or also financial services, if a credit card transaction was declined, you actually want to be able to go in and say like, it was declined because of X, Y, Z, and just saying because that black box said it should be declined might be a bit challenging out there. So this is again, on the analytical side, it's often very simple to argue about why something was declined or why a certain output is there. On the statistical side, it's very interesting research happening there, but it's still an active area of research for explainable GraphML. Scalability. So scalability, I think it's mostly coming in two dimensions. Data size, obviously, but then also how dynamic is my data set? Like how often does it get updated? How often do I need to recompute? And this is a topic of like inductive, where that comes in very handy when I don't have to recompute as soon as my data set changes. Imagine your LinkedIn, Facebook, your graph, even of just user interactions, it's changing like multiple times a second. So that's something where you actually want to be very considerate about how much time you invest in rebuilding a model. Graph Analytics, on the other hand, typically needs the entire graph as input, not just a small part of it. So typically it's really like limited by the size of the overall graph and how easily I can break that graph into smaller pieces to scale. And then second aspect, it's usually transductive by nature, so as soon as like my underlying graph changes, I need to recompute that. As soon as I get a new graph, I need to recompute that. And I think that actually puts us in this choice field, and my argument is actually like, one isn't better than the other. And this is something we are also seeing at ArangoDB. We don't want to prescribe one solution for like all use cases, but we actually see value in supporting one, basically the right tool for your use case. Use Graph Analytics if needed, if it fits your use case. Use Graph Machine Learning if it fits your use case. And have a common platform to actually support that across the entire spectrum. And that's kind of like what we are building at ArangoDB, is basically the Graph Insights platform, like Graph everywhere. And that comes from supports like Graph as a service, so kind of the Graph database aspect we talked about in the beginning. It supports the Graph Analytics aspect we talked about, and it supports the Graph Machine Learning aspect we talked about. So I think all of that, they're basically, it's the same, like I always make the same argument when we talk about programming languages. When should you use which programming language? I think it really depends on the use case. There isn't like one solution for everything, but you need to be aware of the trade-offs, and you need to be aware of when to use what exactly. So this is kind of what we are doing at ArangoDB, and kind of, I actually felt sad that I had to exclude certain slides in here. So let me maybe just jump to the next slide already. But we're actually having our summit coming up in next week, or 2 weeks, October 3rd, October 4th, and they will actually can talk about much more detail about graph machine learning, about graph analytics, and how graph can actually enable various use cases across supply chain, across fraud detection, across financial industries. So feel free to hop in there. Otherwise, we are also at our booth right over there. I think it's 338, so just drop by just behind us, pretty much like 50 meters back, and come over there and let's talk more about graph machine learning, and graph analytics. Thanks a lot for listening. Feel free to come up front if you have any more questions, or just visit us over there. Thanks a lot.